Hello everyone, welcome to the second lecture of this third week where we are going to discuss about order of instruments. This is the second module of this course where we are talking about analog meters, alright. So before we actually jump into the discussion on order of instruments, let us try to understand that from where these orders are generated, okay, what kind of order we are talking about, okay. To understand that, we have to understand the mathematical models of the measurement systems, okay. So if I define a measurement system, it can be defined as a system which is composed of diverse physical devices which are interconnected with each other to measure, to analyze and to control the electrical, thermal, fluidic and other physical quantities, okay. So all these physical devices should be interconnected as well as should communicate with each other, okay. So the ability to analyze depends on how well the characteristic of each components of the system can be expressed mathematically. Say PMMC tool, for example, has mechanical part, okay. So you have a mechanical part here, or forget about PMMC, let us talk about a measurement system in general, okay, which is used, for example, to measure say temperature, okay. Say a physical system or a measurement system which is used to measure a temperature, say, of this room, okay. Now this system will have, say, mechanical part, all right. Say if it is based on certain thermometers, okay, it may have some fluidic or say microfluidic part, right. It has electrical component or say electronic or electrical components, okay. All these three should work independently as well as they should interact with each other, okay. That is how a measurement system actually works, okay. Now if you want to have a proper data, or if you want to get or fetch the correct temperature value, okay, all these things, all these systems which are independent to each other, you should be able to mathematically model them. Say for example, say if mechanical part is, say, certain, say, micro mass is there, okay. Say I am calling it micro mass, okay. It is attached to something. There is certain force because of this string and there is certain force acting because of, say, gravity, or so you have two different forces, say F1 and F2, okay. You have a mass. Now this mechanical system has different components, okay. All these components should be equated or say interlinked with each other using certain mathematical equation, and that is how you can establish or you can develop a mathematical model of the system, okay. So more accurate is your mathematical model, more accurate your predictions will be, okay. However, one cannot directly reach to its mathematical model. First you have to construct a certain physical model, because all these components are basically a physical device or physical component, okay. So the first step to obtain a mathematical model or to model a system is to obtain its physical model, okay. The measurement systems are basically complex in nature, and it is impossible to obtain a physical model of a measurement system which can incorporate all the complexities of the system. So it is nearly impossible to integrate all of them. However, some idealized assumptions are there, some boundary conditions are there which can be made to obtain a simplified version of the system, okay. The model based upon this idealized assumption, keeping in view the specific problem under the study, is basically known as the physical model. So now you have a physical model in hand for the measurement system or measuring system, okay. So once you have obtained the physical system, the next step in modeling is to obtain the mathematical model, okay. Once you have physical system in your hand, okay, say taking the same example, say now physically you know that, okay, this string which is having, say, tensile stress say S, or the force acting is F1, there is a force acting F2 say F1 or F2, any one of it is a say time varying function, okay, say this is mass, okay. So everything you have in your hand, so you have a very accurate by this physical model, okay. Now it becomes very easy at least to develop a crude mathematical model, okay. So a mathematical model, as the name suggests, is a mathematical representation of a physical model and is achieved from the latter by utilizing the physical laws, okay. In this case, for example, the physical law can be say these two forces F1 and F2 if it is in say steady state condition should be equal. So this can be one of the law, okay. Then this, for example, second can be say this force is equal to say mg or something, okay. So there are certain physical laws which governs all these physical models and they can be unified and can be turned into a mathematical model, okay. Of course, you have to have a number of assumptions, you have to have number of boundary conditions, etc., to develop this kind of mathematical model, okay. So actually, if the system of the measurement system has a number of components, as I have just mentioned, it can have say electrical components, it can have mechanical components, it can have thermal components, or there can be some thermal phenomena occurring which has to be incorporated as a mathematical model, okay. So everything has to be taken care when you try to develop a mathematical model, okay. Say consider that your measurement system is having say certain or is utilizing basically a RLC circuit, a series RLC circuit, okay. So the measurement system will have electrical component or electrical network in the form of say R, L and C all in series, okay. In that case, you can develop a mathematical equation something like this, okay. So ET is equal to, in this case, for example, this E is this voltage, okay, is equal to L di by dt plus R IT plus 1 by C into say IT dt, okay. This can be one of the equation, fine. But please note that this is just one representation of the parameters which is being utilized in this circuit, okay. Say if I want to write this equation say in another form, okay, if I want to write in this form of say charge, okay, I can also write it like E is equal to L d square q by dt square plus R d q by dt plus qt by C, right. So the same equation is represented now in the form of charge, okay. So it means that the mathematical model of the measurement system or part of the measurement system is sometime equivalent to another equations. So it doesn't mean that one is correct or one is wrong, depends on what quantity you are dealing with and in which form you want the system, okay. So all you know that this charge, current, all are interlinked to each other. I will not go in that basic, okay. Now similarly, if you have a say mechanical system, okay, so the motion of mechanical elements can be described in various dimensions. It can be described in say for the translational motion, it can be also described for say rotational motion, and a combination of translational and rotational motion is another way in which they can be described, okay. Now the translation is, you know, that is defined as a motion that take place along a straight line, okay. The three basic element in a fundamental translational motion are the mass, and if you are considering the spring, so you have mass, spring and friction, for example, in this case, right. So the mass m, for example, is a internal element of this system, okay. A force applied to a mass produces a certain acceleration, okay. Now the reaction force, this Fm, is equal and opposite to the product of this mass and acceleration by simple equation m cross a, and acts in just opposite direction of the applied force, okay. So if I have to write the equation for this kind of system, I can simply write as Fm equal to m into a is a function of time, okay. So I have to write like this force Fmt is equal to m cross a, which is a function of time, okay, or I can in different forms, say in the form of say position or in the form of velocity, I can write it as m into dv by dt or del square x by dt square, okay, where m is the mass, x is the displacement, v is the velocity, and can be written as the first derivative of the position like dx by dt, or acceleration again is dv by dt or d square by dt square, okay. So depending on what criteria you are using or what quantity you have to deal with in the later stages, okay, you can choose between this acceleration, between voltage, or between the position. Fine. So there can be number of ways in which these mathematical models can be written for particular instrument or part of the instrument, okay. It doesn't have to be complete instrument, it can be written also for the part of the instrument, okay. Now once you understand this mathematical models of this measuring system, okay, it becomes very easy to understand the order of the equipments or order of the instruments, okay. So the order of an instrument is defined basically by the highest order derivative present in its governing differential equation. So once you can write the differential equation for the instrument, it becomes very easy to identify the order because it is simply the highest order derivative present in the differential equation, okay. So it is directly determined by the number of energy storing elements. This is very crucial, that you have to identify number of energy storing elements in the system, okay. This energy storing elements does not have to be only electrical in nature, say for example capacitive and inductive, okay, they will be part of this. However, you also have to look for other ways of storing energy, say for example mechanical masses, okay. So mechanical mass, for example, is part of measurement system. Say this is mass, okay, say it is hanging at a height of a certain value, say h, okay, it is also storing energy. It is in the form of say potential energy, okay. So it is basically m in g into h, right. So when I say that the order of the instrument can be directly determined by the number of energy storing element, you please count the energy storage, say electrical energy storage, I mean passive or active devices, it depends on, you have capacitors, you have inductors, etc., but you also count the mechanical masses, okay. Now we understand two different ways in which I can find the order. The order of an instrument is defined as the highest order derivative present in the governing differential equation of the measurement system, as well as it is directly determined by the number of energy storing elements, for example capacitor, inductor, or say mechanical masses in the system. Fine. So I hope that the basic gist of this order is clear to you, okay. So let's try to understand this with certain example. Say if an instrument uses the RLC circuit that you have just seen, okay, the equation can be written like this, say L del square I by dt square plus R di by dt, say I by C equal to V, okay. Now in this equation the highest derivative is the second order, okay. So you can say that the system is second order derivative. Now if I try to correlate it with the number of energy storage element, let's find the energy storage element in this case, okay. The first energy storage element is this inductor, okay, this L, okay. So this is storing energy in the form of say magnetic energy, or in the it is storing magnetic energy. Now this R is not storing any energy, so I will just ignore this, okay. I will move ahead and I will again find another element which is capacitor, which is storing the charge, okay. So basically it is storing the electrical energy. So you have two different elements in the system or in the part of system. One is storing magnetic energy while another is storing the electrical energy, right. So I have found that this equation has a second derivative, highest order is the second derivative. So I have already commented on its order. I am telling that it is the second order system, as well as if I go by other route, which is by finding the number of energy storing element, I found that there are two different energy storing element, which is inductor and capacitor, and that's why I am also saying by other route also that this is a second order instrument. Okay, so I hope that these things are very clear to you. Okay, now this order also reflects the order of the transfer function, okay, which describes basically the instrument's input output relationship in the Laplace domain. Okay, so if you have transfer function of the instrument written in the form of in the Laplace domain, you can also find it via that. Okay, so highest order instruments shows very complex dynamic behavior, as each energy storage element add basically lag, which affects how the output respond to the changes in the input value. Okay, so let us try to understand this transfer function point of view. Okay, now consider that a simple RC circuit has a transfer function like this. Okay, k by say tau s plus 1. Okay, you can see that this s parameter has a single order. Okay, so the denominator has first order term. Okay, therefore I can say that this is first order instrument. If I go by other route, like the other route is by finding the number of energy storage element, I can see that this is a simple RC circuit, means there is only one energy storage component, which is the capacitor. Okay, so this is another way of looking into the order of instrument. Okay, mostly in this course we will deal with three different kind of instruments, okay, which are zero order instrument, first order instrument and the second order instruments. Okay, so let us try to understand this from different views, by differential equation, by Laplace domain, as well as from the frequency domain. Okay, so differential equation we have already seen, which is of course in a time domain. Okay, so the dynamic behavior of any instrument is first expressed using a differential equation, as you have already seen in the mathematical modeling. Okay, so the order of the instrument is simply the highest derivative present in the equation that we have already seen, and this we are talking in the case of time domain. Okay, so in the time domain, say this is the first order equation. This is a typical equation, differential equation for a first order system or first order instrument. Okay, you have dy by dt. Okay, so first order. Similarly, for second order you have d2y by dt square plus 2 zeta omega n dy by dt plus omega n into yt equal to xt. This is a typical example of a second order. You can simply see that this is a second order differential present over here. Okay. Now, same thing if I try to understand in the Laplace domain, when this differential equation is transformed into the Laplace domain, derivative turns into power of s, as I have already mentioned. Okay, so dy by dt is nothing but s ys, d2y by dt square is s square ys. Okay, so first order, the transfer function for the first order will be something like this, k by 1 plus tau s. Okay, where power of s is 1. Okay, so you can simply say this is first order. Particularly we are mostly seeing this power of s in the denominator. Okay, for the second order, it is the transfer function is something like this, omega n square by s square plus 2 zeta s plus omega n square. If you see the highest power of s here is 1, here it is 2, so it is a second order equation. Okay, or second order measurement instrument. Okay. Now, the Laplace transform shows the order of the instrument as the highest power of s in the denominator. Therefore, the Laplace transform make it very easy to identify the order of the system. Okay, so once you have converted into Laplace transform, it become even easier. Okay, now sometime you have to also deal with the frequency domain. Okay, so Laplace domain, you know that this s is sigma plus j omega, which is a broader complex plane which include both, like including the pure frequency domain where sigma part is the 0. Okay, so you can also think it like by just replacing this s by j omega, the transfer function moves into the frequency domain. Okay, so the output behaves over different frequencies, help us understanding the instrument's dynamic response as well as the dynamic characteristics. Okay, so zero order instrument basically shows flat response in the frequency domain, means the output follows input instantly. Okay, first order instrument shows simple lag and one corner frequency, while the second order instrument shows natural frequency, it shows damping, it can be over damping, under damping, anything, it also shows resonance, etc. Okay, so in graphical term you can think like this. This is the zero order instrument frequency response. You can simply see that it is showing a flat response. Okay, so this is GS is directly equal to the constant value K, means output is following input directly. Okay, for the first order it is in the Laplace domain, it is something like this. Just replace this S by J omega, you will get it in the frequency domain, right? It shows lag and one corner frequency, right? And this is for the second order instrument, and typically this graph shows say zeta value of around 0.3 and this omega and certain value. Okay, so this is a typical response, frequency response for a second order system. Okay, now let us try to understand the transfer function for different order instruments, because we have to deal with this a lot in this course. Okay, so the transfer function remains constant for the zero order instrument, meaning the highest power of S is in the denominator is basically 0. Okay, the good example for this zero order instrument in the laboratory is the potentiometer, which operates on the principle of potential divider. We'll discuss about potentiometer in this course. Okay, so a potentiometer is basically a zero order system because its output voltage changes nearly instantaneously with the input without any time dependent behavior. Okay, it has no energy storing element, means that it doesn't have any say, you can simply see that it doesn't have any capacitor or inductor, or it doesn't carry masses. So its governing equation contains no derivatives, making it a zero order, very simple instrument. Okay, so basically, as I have already mentioned, that we are talking about the transfer function, and this output is directly following this Vi, or if you want to replace it with some constant, it is V0 equal to K Vi, or V0 by Vi is K. Okay, so both input and output have exactly the same waveform. All right. So this is very, very important, particularly for the zero order instrument. Now let us see a little more complex system, which is the first order instruments. Okay, now the first order instrument has one energy storage element and shows a gradual exponential response, particularly if you take a test input like a step input. Okay, so the transfer function is something like this. Okay, so for a unit step, if your input is say ut, in the Laplace form you have Rs as 1 by s. So the transfer function was like this, k by 1 plus tau s. So if you try to find the output, Cs by Rs, okay, or if you find the output, it is the transfer function into the Rs. Okay, so basically the value is k by 1 plus s tau into the Rs, which is the Laplace of this ut function, okay, which is nothing but 1 by s. So output in this case is k by s minus k by s plus 1 by tau. Now if you try to find this in the inverse Laplace transform, or if you want to find it in the time domain, the output is simply k into 1 minus e power minus t by tau into the ut. Okay, so the example of first order instruments are a lot, like the pressure instruments, like electrical measuring systems, which is having one energy storage like capacitor, or for thermal instrument where thermal capacitance is one of the energy storage element. Okay, the first order instrument primarily store potential energy either in the form of, if it is a say mechanical tool, it will store in the form of mechanical strain, or if it is a certain thermal instrument, it will store in the form of heat. Okay, Now if you see the second order instrument, these instruments are little more complex, and ammeter, voltmeter, wattmeter, these instruments which we have to deal a lot, okay, actually falls under this category. Okay, so when analyzing their response behavior, these instruments, all these analog instruments generally act as a second order dynamic system. Okay, it will not stop immediately. If you are talking about pointer based system, okay, and it say if this is the final stage of this pointer, it will try to oscillate around its position, and this is a typical behavior of a second order instrument. Okay, the standard transfer function of a second order instrument is like this, okay, where the CS and RS are the output and input. This is equal to omega n square by square plus 2 zeta omega n s plus omega n square, where this omega n is the undamped natural frequency of the system. This zeta is basically the damping ratio, okay, and based on the value of this zeta, you can have a number of system, like the response can be undamped, underdamped, critically damped, as well as the overdamped. Okay, so when this value of zeta is 0, okay, this zeta value is 0 means the system is omega n square by square plus omega n square, okay, and this type of response is basically in this case is undamped. Okay, now the system oscillates continuously in this condition with no decrease in the amplitude. Okay, now when this zeta value increases a bit, however it is less than 1, okay, the system is known as in the condition of underdamped. Okay, and in this case the output shows oscillation, but the oscillation gradually die out with time, and this is the condition basically we mostly achieve. Okay, now when this zeta approaches to 1 and it becomes 1, okay, the system is said to be, or the response is said to be the critically damped response. Okay, in this case the system returns to the steady state as fast as possible without oscillating, and this is kind of ideal condition. Okay, now when this zeta value crosses this 1 unity value and it becomes greater than 1, this condition or the response is known as the overdamped response, and there is no oscillation, but system responds very slowly and take longer to reach to its final position. Okay, so you will be reading more about this second order instrument and all these damping values when you cover the control system course. Okay, so in most indicating type measuring instrument, the system, as I have already mentioned, is underdamped. Okay, as a result the pointer oscillate for a short duration before it gradually comes to its final steady position. All right, so this is about different orders of the system. Okay, now let us talk about different errors that are feasible, particularly seeing from the instrument point of view. Although if you remember, we have covered error in little detail when we talked in the module 1 about different noise and different errors. So if you remember, we have discussed 3 different errors. One was the gross errors, mostly because of human error, and then second was the random errors, and then we also discussed about systematic error, which include 3 different errors like instrumental error, environmental error, and the observational error. Okay, this instrumental errors is very crucial, and there are certain instrumental errors which are very specific to this electromechanical indicating instrument. So let us try to understand what are the errors which are very specific to this indicating instrument. One is the frictional error. So friction between the moving shaft, because you have seen that there is a moving shaft in this case, and the bearing basically introduces a measurement error in the indicating instrument. Okay, the frictional force basically can be given as F equal to this mu n, where mu is the coefficient of friction and n is the normal force. Now as the instrument's weight increases, this n value increases, because this is the force, or say normal force acting because of this weight. Okay, and the frictional force has to be increased because this has to balance this n. Okay, so F is equal to mu n, and if you are trying to keep this constant, and if this is changing means this has to change. Okay. So to minimize the frictional error, the instrument should have a high torque to weight ratio, which will be ensured by this condition where this Td is the deflecting torque and this is the frictional torque. Okay. So by this condition, the frictional effect can have negligible or at least minimum effect on the final reading. Okay. Then we have temperature error. When the temperature increases in the measuring condition, the resistance of the coil also increases. Okay. As a result, the current through the coil basically decreases. Therefore, the instrument's indication or reading becomes lower than the actual value which it should have shown. Okay. So we have to take care of this temperature error. And the third kind of error which is specific to this indicating instrument are the frequency error. When the supply frequency basically increases, the inductive reactance which is present in the form of say 2 pi FL also increases. Okay, particularly for the inductors. Okay. Now this causes the total impedance of the circuit to increase, and because of that the coil current falls. Now the instrument reading drops when you try to increase the measurement frequency. So while taking the measurement, all these three kind of errors has to be taken into consideration. All right. Now this is what we have to discuss in this second lecture of this third week. In the next class, what we will talk is mostly regarding the construction of a electromechanical indicating instrument, because the construction is very important and the foundation behind all the electromechanical indicating instrument like PMMC, moving iron and all that we are going to discuss in the next modules. Okay. So what we will do is we will talk about in very nutshell about the construction of these instruments, and then if the time permits we will also talk about the fundamentals of ammeter and voltmeters. Okay. Then followed by a discussion on the galvanometer. Thank you.